Algebra 2, here are some notes on parent functions and transformations, and this is just part 1 of the notes. So the first thing I want you to do is just a little exploration. So if you're watching this video, you're probably not able to work with a partner, but I want you to do this on your own. So you're going to, some of these things you're going to know from your prior math classes, but some you won't. I want you to classify each of the graphs below as one of these functions. So either as a constant function, a linear, an absolute value, a quadratic, a square root, a cubic, a reciprocal, or an exponential. So use your past math knowledge. Some of these functions you will know, but some are going to be new to you. So in that case, you can just use process of elimination. Pause the video and see if you can match, and then write the name of the function in the space below each of the graphs. When you're done, unpause the video and we'll go over these together. All right, let's go over each of these functions. So if you look at A, that is a V-shaped graph, and this graph indicates an absolute value function. So absolute value equation is like a line except for the absolute value part of it. And you know, because we covered it in the review, that the absolute value is the positive value. So it makes sense that there is no graph covering in the negative part. B, this is a square root. And so if you think about taking the square root of a value, you're going to get a positive number. So that's why this graph is in the positive quadrant of our graph space. So where our x's and y's are both positive. C, now you might have put linear, but more specifically, this is a type of linear called a constant function, where y will equal just a number, and in this case, that number is 1. D, you've probably seen a lot of these in the news over the last 6 months. This is an exponential graph, where things are increasing exponentially. E, this is a cubic graph. F, this is what we would call our linear. G, you might not have seen this graph before. Both parts make up the graph, and this is a graph of a very basic reciprocal function. And then finally, hopefully you recognize the graph of H as a quadratic. So what we're going to learn in Concept 2 is just some basic parent functions. Functions that belong to the same family, they share key characteristics, mainly the shape of the graph. Not always are they in the same location on the graph space, but they'll always have the same shape, basically. The parent function is the most basic function in that family. And so you need to become familiar with the parent functions that are listed in the table below and their function shape. When we have graphs that look similar but are in different location, those are in the same family. Those are called transformations of the parent. So another thing is that if you look in our table at the very bottom, you'll see domain and range. So we're going to talk about the domain and range of each of these equations and graph. A domain, and I'll go back to that in a second. So first I want to point out that parent means the most basic function in the family. And then just as a review, when I use the word function, that means an equation, and usually we have between two variables, x and y. For each input, there is only one output. And when you see function notation, like this, f parentheses x, you will read that and say f of x. F of x just stands for y, the output. All right, now let's talk about domain and range. So look at that bottom row in the table there, and you'll see domain. Domain means the possible inputs that you can plug into this equation to get a real number output. The range is the set of outputs that you will get after you put those inputs into the equation. All right, now let's go through these parent functions. So the first one is called a constant function. The most basic or parent of a constant function is f of x equals 1. Transformations of this would be f of x equals any real number. All right, and then the graph looks like you see below. I'm going to be a little picky and show you that I like to put arrows on these because these graphs do not end. They are not segments. They are lines. They will continue in either direction, positive or negative. The domain of a constant function is all real numbers, and then the range in this case, even no matter what value you plug in for x, you will just get y equals 1. Now, linear function is f of x equals x or y equals x, and that's what the graph looks like with the arrowheads on it. You can plug in any number for the domain, the x values, and you can get any real number y out. Absolute value is a V-shaped graph. There's no curve in this graph. It's like a line that comes down and then switches direction. In equation form, it's y equals, now that should say absolute value of x, so I'll add those little marks. There we go. And then you can plug in any value for x, and you will only get positive values or 0 for y, so that's why our range is limited. Quadratic function is f of x equals x squared or y equals x squared in equation form, and that's what the graph looks like. We call that a parabola. You can plug in any real number for x into this equation and you will get only positive or 0 values out. Now, a few things that I'd like to point out is with linear absolute value and quadratic functions, notice that they all intersect the origin, 0, 0. And they have, the absolute value and quadratic have limited range, and that is because of the math in the function. So when you take the absolute value of a number, you will only get a positive value, so that limits your outputs. Quadratic, when you square a positive or a negative number, you only get positive outputs, so that limits your range. All of these basic graphs and functions you need to commit to memory. Also, their domains and ranges. I always think of it just logically with domain and range, because then we're going to be talking about and graphing transformations. So you'll want to, in your mind, have the basic parent functions as a reference point. All right, and then let's do that. This is graph g of x equals x minus 4 in its parent function. Well, right away you should recognize that's a linear function. So the parent function of a linear function is f of x equals x. So let's quick make an xy table and then plug in values. So x equals y, so our x and y values will be the same. You can see I'm graphing them on our graph space, and that should look very familiar because we were just looking at the parent function of a linear equation. Now, in the table, let's graph g of x equals x minus 4. Let's plug in values for x and then get those values for y. We plug them into the equation, and let's graph it. So negative 5, negative 9, 0, negative 4, and 5, 1. And so you can see that this is a line that has been shifted down 4. What do you think would happen if we had the equation g of x equals x plus 4? Well, I bet you can guess that would shift our parent linear line up 4. Let's look at another one. So we're going to graph p of x equals negative x squared and its parent function. Well, you can tell that the parent function is a quadratic, that f of x equals x squared. Make a quick xy table. I just plugged in negative 1, 0, and 1. When you square them, you get positive 1, 0, and 1. When you make a graph, you always want to draw in your x and y axes. You want to label it and label a scale. I will do that every time and expect you to do that every time. And that's the parent shape. That should look familiar. We were just looking at it in that table. So now let's graph our p of x function. So it has a negative sign. So if we take negative 1 and square it, we get 1, but then we have to make it negative. 0 is 0, 1 is negative 1. So we'll plot those points and then draw the curve. And you can see that this p of x has been reflected over the x-axis. So now we're just exploring some transformations when we start introducing other numbers and signs into our parent equation. Take a look at these two. We're going to graph each of these equations and its parent function. So g of x equals 2 times the absolute value of x. So that means our parent function is f of x equals the absolute value of x. Now, I'm not going to make a table. I'm just going to do this in my head. So when I plug in -1, take the absolute value, it's +1, 0 is 0, and then 1 is 1. And there is the graph of our parent absolute value function. Now in the table, I will write our g of x function. So the absolute value of -1 is 1, times 2 is 2, 0 is 0, and 1 is 2. So graphing these points, I had a little trouble with this. I was trying to get it just right. But you can see now we have a graph that is skinnier. That too makes our y values twice as steep. So we call that a stretch. Now h of x equals 1/2 x squared. You can see I didn't pay close attention because I treated this one as an absolute value. So we'll just run through this and then I realized my mistake. And there we go. All right, so our parent is actually f of x equals x squared. I'm not going to make a table. I'm just going to graph that. So I know if I plug in -2, I get +4, -1, 1, 0, 1, 1, and 2, 4. So there's the parent quadratic graph. And in my table, I'll put h of x. I'm just going to plug in -2, 0, and 2 for x. And then when I put that into the equation, I get 2, 0, and 2. Plotting those points. Now, see how that red graph is wider? That's what we call a shrink or a compress. So those ends have been compressed down towards the x-axis. I will use both of those terms because you will see both of them. Now, predict what's going to happen to the graph g of x equals negative times the absolute value of x plus 5 minus 3. Well, I bet you remember with a negative, that means that this graph, which will be a V-shaped graph because its absolute value will be reflected. Because we have a 5 added into the x, that's actually going to shift it to the left. And we'll talk more about that in later concepts. And then the -3 is going to shift it 3 down. All right, that concludes part 1 of our concept 2, which is parent functions and transformations.